we've asked Alexi to cover this session for us. As we all know, in South Africa, it is quite a new area for us. It's still a lot of learning. There's still a lot of research being done. So we actually requested Alexi to start and open all the discussions for us a bit on the hydrogen solution and how Ansys can really support us moving forward. What we will also do is open a poll where we will be asking some questions in the chat. You don't need to answer it straight away. You can answer it later on, but it's just to guide us in terms of what is your requirements, what you are interested in, and what we can follow up on moving forward. What I will do is start the poll shortly, and then we'll also start the recording.
Okay.
Just hold on. Okay, great. So over to you, Alexi. Thank you very much again, and you can continue.
Okay, thank you, Laura, for the introduction. Thank you, everybody, for joining. Hydrogen is typically a very vast subject. It has been around for quite some time. Hydrogen-related technologies, we dealt with them for a number of years, but they also experience a certain shift as we go into the green hydrogen when we want to produce it in the most environmentally friendly way. So as Lara said, we open a poll so that we get a bit more feedback from you, from the audience, just to see which particular subject is of more interest to you so that we can do deep dive sessions later on or take it to a different level. This particular presentation is a broad overview of what's involved. As I said, it's a very broad subject, so it's difficult to cover everything in depth. But typically, when we look at hydrogen, firstly, yes, it's something that is not freely available. One needs to firstly produce hydrogen, and this is something that requires a lot of energy. And when we look at the energy input, there are different types of it available, whether we're talking about nuclear power, whether we're looking at... Sorry, so there are different types of power that can be used to store it. I think Africa generally, in a very, especially coastal areas, are in a very sweet spot for it, because when we talk about the green hydrogen production, so typically, well, we would like to use the energy which is readily available. And in Africa, you do have lots of solar power. Every day, so Earth receives 60,000 times more energy than the humankind consumes. So effectively, harvesting that would be of great importance. And if you have lots of sun, if you get lots of water, like in coastal areas, you can easily produce hydrogen in abundance by means of concentrated solar power. But anyway, so in other parts of the world, so for example, in Europe, maybe in the southern tip of Spain, we can get concentrated solar power, but anywhere else, we need to revert to other means of using energy input. And this is something that we cover. When it comes to the actual production of hydrogen. So there are different types of it. And if you look at this diagram, you can see different means of getting. Typically, most of the production goes through the until now, maybe it was mainly from the steam methane reforming. So or through the sort of other means of conventional gasifications of via pyrolysis. So now, as we sort of towards in the beginning of this century, so we can see a gradual shift to using electrolysis for hydrogen production. In the past, it existed, but it was less common. And but this is something that allows us to produce hydrogen in the most efficient way, energy efficient way. So, but once hydrogen is produced, one by certain means or the others, so we need to somehow storage and transport it, and we need to condition it before that. So yeah, it can be done either via compression, or we need to liquefy it, or we need to store it in some sort of chemical or physical absorption form, or just create a synthetic fuel out of it. So this type of this is a separate subject which requires a lot of effort, and not effort, but it requires lots of attention, because we are dealing with a either very low temperatures or incredibly high pressures, and that poses certain challenges. So that challenges are present not only in the point of storage, but also in the point of transport. So when we ship things, when we create pipelines or rail, so all those conditions needs to be satisfied, and the hydrogen that needs to be safely stored. Also, so there's some challenges with storage and transport. If the accident happens, sort of there are a number of accident mitigation measures that needs to be taken, and they also can be simulated. So those processes. Nevertheless, once the hydrogen finds its way to the end user, so we need to utilize it. And how do we do that? We have combustion. That's something that's been used for quite some time. Burning hydrogen as a fuel. Now we have either in a pure form or as a blend with methane, or we can use it in fuel cells, for example, when you can convert hydrogen directly into water produced by producing electricity. So this is fuel cells are not new technologies, but they've been around for quite some time. But the commercialization of them started just in early 2000, and now we see wave of a second massive wave of fuel cell production. So when we look at different modeling aspects, so when it comes to production, we typically need to address whether we do steam methane reformer. We need to model or exact the device that will do that. If we use electrolysis, that's a very different process. That it's not only the chemical reaction that takes place there, so it's electrochemical reaction that would be present there, and there are different layers usually within the electrochemical devices with different characteristics, with different dynamics, and this is also something that we need to cover. When it comes to storage, we need to store it in under specific conditions. We also need to be aware of material embrittlement. If it's effectively composite material, that also needs to be accounted for and modeled in a specific way. When it comes to transport, as I mentioned, it's accident mitigation. We need to know hydrogen can ignite at a very low concentrations. So this auto ignition needs to be accounted for, and and risk mitigation, escape routes, typical sort of channeling of the flame, all that needs to be accounted for. So, and when it comes to consumption, it's either combustion or fuel cell processes when hydrogen gets converted electrochemically. So all these aspects we actually are confident in covering these days. So let's go back. So typical steam methane reforming. So what usually you need to treat methane and steam mixture at a very high temperature and for example, and high pressure. So these are typical column devices, very long tubes where this reaction takes place. So this takes place, and if we have a look how we can do it, we would like this device to be more efficient and to get the high conversion rate. So on this plot here, you can see when hydrogen has been produced at different temperatures. So what kind of, how experiment shown in blue, and how the simulation, how they compare at for production of hydrogen and all the byproducts that come along with it, so carbon monoxide, carbon dioxide. And we can also see what is our methane conversion ratio in this case. Yeah, so that's something that we can do. But using methane in order to get hydrogen might not be the most efficient way, but established technology, and that has been used, still being used quite a lot these days. So our aim is just to help you minimize the cost of it through simulation. So pyrolysis or gasification of biomass is another thing where effectively sort of steam is being fed through some biomaterial, and effectively that also helps us at higher temperature produce hydrogen. It's a slightly different means, but they, in principle, the process is the same. Or modeling fluidized bed and chemical reactions associated that might be present in the reactor, something that we can confidently cover, and something that we can also optimize, sort of, and get you an efficient and optimized device as a result of it. Needless to say that this processes of gasification is the problem with that is that typically produces lots of byproducts or something that, or sort of gases such as carbon dioxide that are greenhouse gases that will not be particularly welcome in the mixture. So it will not be a very clean mixture. So we have a different tools for achieving that, whether it's Fluent, whether it's Rocky, whether it's OptiSlang for optimization, but we do have solution for actually various stages of that particular process. So when it comes to electrolysis, then it gets more interesting because it's more modern, it's more efficient, it's a considerably greener process of it. You simply need to supply water and electricity to it, and on the outlets you will get, you'll typically get hydrogen and oxygen in a very pure form. But that becomes, for that one needs to model electrochemical reactions. And in Fluent, we do have 3 dedicated electrolysis, not even 3, 4 dedicated modules, 2 modules to model solid oxide electrolysis, sort of high temperature ones, something that usually been used on next to power plants, combined with other technologies. But also we have water electrolysis directly, so as a proton exchange membrane, PEM, water electrolysis, or alkaline water electrolysis. The latter 2 models that have become available in our software in 23R1, so they are just as a release feature, so they are relatively new. Solid oxide electrolysis we could model for quite some time. So it helps you to simulate the process that will happen within the fuel cells, just to see how uniform or non-uniform your distributions are, whether you do have any sort of starvation regions, whether your water gets where it needs to get before it gets converted to gases, so that you don't have ineffective part of electrolysis. So there are a lot comes to optimization and see how electrolyzer performs under different conditions. For latter 2 types, for PEM water electrolysis and for alkaline water electrolysis, it's also important to model the multi-phase aspects of it with a great accuracy, because you do have saturation and capillary pressure is the driving force that will drive the water to the reaction zone, and there are a lot of optimization needs to be done so that you don't clog, that you don't starve the area without water. If you cannot remove the produced gases away from the reaction zones, the electrolysis will not be efficient. So there are some differences. Effectively, these type of electrolyzers, they are fuel cell in reverse, but not quite. So certain changes to the design are required for these devices to be efficient. Since here you can see this is a polarization curve, sort of cell voltage, electrolysis cell voltage, and the current that needs to be supplied at different voltages, and then you can see that we have experimental data, and we do have the multi-phase modeling effects of it, and we can see that if we account for the multi-phase aspects consistently, then we can predict the polarization curve consistently. In other words, we can model electrolysis under different operating conditions. So, and this is typical device. If we can take the most simplistic form of it, we can see, so effectively, yes, we supply water, but we can see how it's counterflow design, and we can see that we start producing gas, and towards the outlet, we'll get more and more of, in this case, hydrogen on the cathode side and on oxygen on the anode side. That's what we'll get. So there are different aspects to it. It's not only CFD, it's also structural analysis to it. There is also system level simulation. There is also, and even within the CFD, there's so many facets to physical modeling. But I can talk for another hour just on that topic on its own. So when it comes to, let's just focus for the time being on the high temperature solid side electrolysis where we don't have multi-phase issues, but we do have very high temperatures in this case, and we need to mesh those devices very accurately. They usually have certain great amount of details. Sometimes we resolve them explicitly, sometimes we don't. We use porous media approximation. But anyway, so when we solve it, we would like to see how uniform different our distribution within the electrolyzers are. So it's just the more uniform, the better. So then it will imply that more efficient usage of the active area is achieved. And also, because it's a high temperature, we also need to account for any structural stresses that might be present in the domain. So that's where fluid structure interaction can be of particular importance, because at those high temperatures, you don't want to have massive distortion. You don't want to have leaks in your domain because, okay, hydrogen and oxygen mixed together, it's not the good mix. Yeah. So there are a number of safety aspects and device efficiency aspects that needs to be covered with that. So when we move to production, so no, when we move from production to downstream stages for transporting it, so there are a number of issues associated with that. So as I said, there are a number of safety studies associated with that. And the problem with hydrogen, the molecules of hydrogen are so small when they get into the crystal structure of the pipes and vessels that store and transport hydrogen. So we see that there's a process called structural embrittlement of the materials that hold hydrogen. So the properties gradually drift and become less and less capable of withstanding specific loads. So this is something that needs to be sort of accounted for. So if structural aspects by using mechanical products or structural aspects of it, where there's fatigue, where there's stress propagation, where there's crack propagation, and from CFD side, so when leaks happen, as to how they're going to happen, where they're going to happen, what kind of consequences we might have as a result of that. So interestingly, so typically when we look into all these technologies, they are not really hydrogen directly related. They are we currently have all this technology already been present for LNG, for liquefied natural gas, but we cannot just simply adopt them for hydrogen. Hydrogen imposes much stricter sort of or tighter requirements for all the same thing. But the technology is not new. It just needs to be fine-tuned. It needs to be polished. It needs to be adjusted for the new gas. And that's where the Ansys solutions become very handy in assessing the differences and optimizing them for storing and transporting hydrogen. So here is just an example of the structural integrity. So if we do have a crack growing somewhere or sort of being present in the pipeline, so when we can account for the stress distribution across alongside of the pipe and just to see what kind of difference it will have when we move from compressed air to having hydrogen that's going to be present in the domain. So for that, we typically use Ansys Mechanical and code, and for optimization, we use OptiSlang as well. So, and we can come up with the failure assessment diagram and this can help just mitigate the issues. If not mitigate, at least we will be aware of them and know where to expect them. So when it comes to compressing designs, yeah, that's also an interesting subject because compressors, all of those are well-established technologies. We do compress gases we have been compressing gases as humankind for a very long period of time. But hydrogen, once again, is a moving part. There's embrittlement. It can escape quite easily. You need to have hydrogen can ignite at a very different stoichiometries with air. So from that point of view, making all those assessments are quite important. But these are here is a typical workflow, sort of what we can do for optimizing that and for solving that, for avoiding leaks. So these are well-established technologies. There's not much different from what we do already for other gases. Just with only thing in mind that our margin for error is much smaller when we deal with the hydrogen, and certain things needs to be optimized for having this gas. When it comes to storage tanks, whether they are cryogenic liquid hydrogen or whether they are compressed hydrogen, typically, just to make it a viable option, it needs to be a composite material. And we would like to have it as lightweight as possible. So, for example, these days, we know that we can even see some hydrogen cars become commercially available, and Toyota Mirai, I think they have a car, and they've got 3 composite material tanks, and all 3 of them store hydrogen at 700 bars. It's a compressor, it's not liquid solution, but it's a very serious pressure that we are dealing with. So once again, if we compare methane, if we take propane tank, it's 10 bar. If we take methane tank, it's 100 bar. If you take hydrogen, it's 700 for it to be sort of suitable for the automotive industry. And withstanding these pressures is something that requires simulation. It requires rigorous testing, and that's where our Ansys composite pre-post our structural tools. That's where they would become of a paramount importance, just to make sure that everything is calculated consistently and there is a safety factor that's built, significant safety factor that built into the model without any particular critical spots being present in the tank. So, but if the leak happens, and they do happen during fueling, refueling, and due to some cracks that happen, so we need to bear in mind. So when we deal with this type of pressure differences, we will have under expanded jets being formed because due to it with all the shock diamonds and things like that. So dispersion of it and the momentum that the jet gains in comparison to normal leaks of methane, for example, is quite different. So that needs to be accounted for consistently too. So that's where our CFD solutions would play a major role and can be of great importance to anybody who's working with that. Um, so should the flame ignite? Yeah, that's once again, it's still a CFD. So this is something that would allow one to simulate the flame propagation or explosion that might take place, just to see where it's happened, directionality of it, whether there will be any escape routes, whether it's possible to escape. So all this needs to be risk assessed, and that's where it can be of a paramount importance. So when it comes to utilization of it, then we typically, until now, most of the hydrogen was just burnt. Typical example is the rocket nozzles or rocket engines when lots of hydrogen, liquefied hydrogen, has been sort of burnt, and for that, typically it's a chemical reaction and it's flow, it's heat transfer, or typically real gas. It's a very high pressure difference. So for that, and so once again, that's where our CFD technologies and our combustion models and turbines model become of paramount important, and that's what we can calculate consistently with a great degree of certainty. When it comes to combustion of methane and hydrogen blends, that's a separate topic where a lot of attention is being played now. If we look at the UK, for example, infrastructure, gas infrastructure, methane, typically there's a gas methane being supplied for domestic and for industrial use. But since for the last 10 years or so, hydrogen started being blended into the methane stream, but that changes the characteristics of the mixture of fuels, and that poses certain risks. So in typical domestic boiler, for example, that installed in most of the British houses, one needs to be aware so that you cannot increase hydrogen concentration above certain, I think it's 4 or 5%, so that you don't have any issues that the flame would escape in the burner upstream and cause damage and explosion. So that's the thing. But nevertheless, for that's something, every one particular example of risk assessment. But if we look at power generation, for example, that's where a much greater blends have been used for with much greater hydrogen proportion. So in this case, methane hydrogen mix is being fed directly into the gas turbine, and that you, and use just the way it is, because in this case one can control combustion mechanism. But still, burners of the for hydrogen combustion, if we use hydrogen, or if we use hydrogen methane blends, those needs to be different. They need to be tuned. Certain orifices, certain sort of injection parameters, they need to be adjusted for the device to work efficiently. And that's, once again, that's a CFD. That's another aspect where we need to account for it. The energy release is also a bit different, so some optimization for that, or some extra requirements for the materials also needs to be accounted for. So this is once again where Ansys Solutions can be can highlight the potential problematic areas before they become an emergency. So that's some reassessment. A lot of reassessment needs to be done for the existing technologies that exist for methane infrastructure. So when we look to hydrogen fuel cells, similar to electrolysis, so this is it's not new, as I said. Fuel cells have been around from 1870 or something like that, but they only became, then they were known in the 20th century a little bit for specific bespoke applications, but now they're becoming mainstream. So they get used more and more, and different types of fuel cells, and they're much more efficient than the any IC engines, for example, much more efficient, and therefore they're very appealing, and they use hydrogen directly. So it's all very environmentally very friendly. So, but when it comes to modeling fuel cells, once again, we do have different layers. We do have membrane, we do have catalyst, we do have gas diffusion layers, microporous layers, bipolar plates, all the different aspects. So it looks like a simple sandwich, but in this sandwich, there can be from 7 to 11 different layers being present, and all of them with different characteristics. Electrochemical reaction will happen in the catalyst side, and we would like to ensure that the design of fuel cell is such that we use the active area in the best possible way. So for that, we typically use Fluent, where we do have bespoke add-on modules for proton exchange membrane fuel cells and for solid oxide fuel cells. So this is something that we had already for a good 17 years or so, and the models have received significant amount of for the development in the last 4 or 5 years, when the second wave of fuel cell uptake has taken place. So if we look at it, so this is a typical example that shows us what happens with the mole fraction of hydrogen across different channels, where it's higher, where it's lower. So ideally, we would like to make it as uniform as possible. It's not an easy task, but most importantly, we would like to avoid areas of starvation. So when if there's certain area which of active area which is not receiving amount of hydrogen or oxygen on the cathode side, for example, then these areas tend to become, it's not only that we are not using active area efficiently, but these areas tend to become very hot, and that's not good for the longevity of the fuel cells. And fuel cells are we still going into the mass production now, but they are not cheap at present. It's improving, but they're not cheap. So the number of aspects, CFD part of it, electrochemical part of it, we can model it. There's a structural aspects to it, but there is also uh, longevity of them that is quite important to assess and to see where things are going, or just to choose the operational envelopes in such a way that we do not have that we do not affect longevity adversely. Also, sort of, we have multi-phase aspects in there. So if you do have hydrogen and oxygen combining together, so we'll have water vapor. And under certain conditions, if you put your foot down in a car, and if your car is fuel cell driven, so if you try to extract more power out of fuel cell, then you might encounter conditions where that water will start condensing. And that's, once again, that's a multi-phase issues. There's some multi-phase issues that affect performance of the fuel cell, longevity of the fuel cell, and once again, it requires optimization. So if we look at a typical fuel cell, we are dealing with probably 150 parameters only with the materials and different properties, let alone any geometrical changes to it. So it becomes very multi-parameter optimization problem. But it's very interesting, and it's mainstream. It really grabs attention these days, becomes very important. So when it comes to fuel cell, it's not only about the fuel cell itself. We do have a balance of plant. So fuel cell is not like battery where you have typically store energy and then you consume it until the battery is depleted. Sometimes you need to cool batteries, but with fuel cells, it's more complex than that because we do supply hydrogen and we do supply air into it. It needs to be cleaned. And also, so when we put the hydrogen through it, it needs to be, we do not achieve 100% utilization because that will lead to local starvation. We typically have some hydrogen on the outlet from the fuel cell, but we don't want to throw it into the environment. We need to reuse it. So we need to separate it. We need to feed it back into the stream, back into the fuel cell. When the when the on sort of oxygen stream comes out of it, it becomes very humidified. Sometimes we can discard it, but sometimes we need to reuse that water. We want to reuse it and humidify the oncoming hydrogen stream. So there are some sort of condensers, there are some humidifiers, dehumidifiers, lots of valves, lots of compressors. So it's called balance of plant. So to model all of that, we need sort of a system level approach. And for that, we use a specific fuel cell libraries within the in Twin build itself. If you want to account for the system level approach to it and see how the whole system operates as well. So coming back to our original slide, so what we have, so we have here sort of coming back to from production to utilization, all of different aspects of it, and all of it we just cover. There's one thing that I didn't mention, say, for example, like concentrated solar power, for example, you need energy to produce hydrogen. And so if you look at solar plants, all the ray tracing, all these masts that you can find somewhere in Africa or in Gulf countries, so these are, and in Spain. So this is something that also can be covered by us because these type of technologies we can address with different tools, not only CFD, not only heat transfer, but also optical tools for ray tracing, amounts, so solar calculators and things like that. So this is something for you to be aware of it. So I think this is it from me for today, but it would be great if you could fill the poll just to tell us what your particular areas of interest so that we can focus on those areas and to have a deep dive session and explain nitty-gritties of each individual area in a greater detail.
Okay, so thanks a lot for that, Alexi. I think it was very, very good. I think that there's a lot of interest, and I can see there's been a few who's already answered the poll. But before we get to that, there's a few questions as well.
Sure.
So I'll just go and have a look in the chat. You can unmute yourself by now, and then you can ask your questions. Okay, one was about the presentation. We will share the presentation and the recording afterwards. Then there's whether Ansys can be used to simulate H2 diffusion through the shell of a pressure containing equipment. For instance, pressure vessels.
Yes, it can be. The problem is that it's a very slow process. So there are you can simulate it, but you can have you can assess it. It's not really a particular problem. You need to be aware that it's typically um, fairly long process, and assessing the exact time as to at which point in time what kind of hydrogen concentrations you'll get within the metal structure. This is something that might require a bit of attention, a bit of tuning, but it's possible.
Okay, so Oscar, in essence, it's possible, but a bit of tuning. Let me just see.
Just in terms of assessing of diffusion coefficients and so what they were going to be.
Okay, then there's one small modular reactor.
No, it's a steam methane reactor.
Okay. Yeah, Mustafa, we'll get back to you on there's been a request about the presentation and tutorials. We'll be able to share that directly. Yeah, then there's just questions about they will be interested to see how Ansys can support the hydrogen in the production area. I don't know if there's anything specific that you want to cover on that now, unless we can just follow up that afterwards.
For production, I think in a way we do have some material, but electrolysis came a bit later than the fuel cell technology. So we are getting some material that we can share. But if you look at Ansys Learning Hub, we do have certain material available here. You just go under the fuel cells, and there's some electrolysis material there too.
Another question. Kevin, do you want to ask your question perhaps, or okay.
Yeah, so sorry, just for me the presentation was quite complex, Alexei. So I just wanted to find out, in comparison to what is actually happening in industry, it seems that industry is still getting to learn and adapt to the knowledge of hydrogen and energy in this field, but the knowledge presented is very advanced. I just wanted to find out, when you've spoken to scholars and engineers, how far have people gone to the extent in terms of simulation knowledge and trying to build a hydrogen system? I think a lot of people are still learning, and your presentation is very, very advanced and complex.
It's just the scope of it is very broad. Yeah, that's why, because I was going from one subject to another. And I only had 1 or 2 slides for each of them to show. But if you look, typically people don't look at the whole cycle from A to Z. People look from A to B or from H to I and things like that. So it's not really, people look into it more and more. It's definitely on the rise. There are certain challenges when you simulate those type of processes, but typically also you will discover that people who work with electrolysis and people who work with fuel cells, they are not necessarily the same people. They might work for the same company, but there would be different dedicated groups. People who work with combustion, they've been working for it quite some time. People who start looking into the hydrogen combustion fuel, they have a lot of experience with the methane combustion, sort of in the gas turbines, for example. Risk assessment, exactly the same story. So in principle, technology is there. People use that. It's just they need to make a shift, and they need to be people are trying to get used to that new things and the challenges that that shift brings.
Okay, thanks.
But it's happening, and it's happening everywhere, both in academic environment and in industry. And if, say, for example, 10, 15 years ago, it was primarily academic interest or some research establishments that look into it, maybe a few, very few industrial ones. Now it becomes industrial mainstream.
Yes, I think from South African point, I think a lot is currently being done on the research and that initial beginning phase. Some commercial clients are taking it up, and they are putting the research in place for the equipment and the manufacturing side of things. But it is a new initiative within South Africa, and hence why we can take the learning from our Ansys colleagues and the rest of the Ansys to support the South African audience to really help them to drive this forward. So we are open for any questions. Doesn't matter where you start and where you are in your journey. But we've got the expertise and the know-how to support it and to help you drive it forward. I think there's a question from Robin. Do you want to ask your question? I think she's just, or the person is just referring to saying that
Okay.
in industrial practice, there are theoretical, experimental, and practical inputs, including process data and material and transport properties. So I think that's just Robin's
I think it's a comment to
to what we were just discussing. So anybody else? Any questions?
Hi, sorry, I think I have my hand up.
Yeah.
I'm Kuvir Murli. I'm from the University of KwaZulu-Natal. We are clients of Ansys. I wanted to ask, when it comes to, well, our particular interest is in green hydrogen, and an area that requires a lot of research and attention now is the PEM membranes and the longevity of these membranes, their destruction over time and stuff. And I feel that this software can be used particularly for modeling, not necessarily the performance of the membrane for hydrogen production, but just its sort of longevity and how it changes over time. At the moment, we have very little information on how these PEM electrolyzers work, the quality of the water that affects the membrane and stuff like that. So, could you maybe comment on how on if there is work in that area or how that can be improved?
So in principle, yes, because in principle the materials, they deteriorate with time and their properties change. So for as long as we account for that property change consistently, we can still see how that device, whether it's fuel cell electrolyzer, how they would perform as the time goes by. However, having the accounting for the mechanism as exactly how these properties are drifting, this is something that we do not have at present. So this is something that is currently an area of academic research. If there are any sub-models that can account for aging of it or changing
Yeah,
of
for
it,
sure.
of their characteristics, that can be relatively easily implemented. But usually, yes, okay, you would. But it will give an indication how this property is drifted, so that you can perform a CFD simulation of it with the new set of properties. But longevity itself, that's a bit of a problem, because I think I haven't seen any model or graceful model that would allow to do that. To do that type of assessment, or it becomes an empirical. Then one takes that empirical correlation and does some hand calculation and feeds it back into the software to perform a simulation of the fuel cell performance under changed properties.
Yeah, thank you very much.
I think there's another question.
Yes.
Hello.
Yeah, hello.
Hello. Hi. Actually, I want to know that in green hydrogen plants where we use the alkaline electrolyzer, can this NCs be used to model the part load behavior of the electrolyzers? Because at part loads, normally we face the problem of, gas diffusion, the hydrogen in the oxygen sides, and if it goes above the explosion limit, it's a problem. So this is the problem we usually face. And then again, how far the load, when the load changes from let's say 10% to 30%, at what, how much duration it will take to stabilize. So these all data given by the manufacturers, but to validate that one, can the NCs be used?
Yes, it can be, because whenever you are in the polarization curve or any operational point, you can simulate those scenarios. You can simulate them in a transient way, how you go from one to another, and you'll see how the species, what are the inertial effect with the sort of reactants of the reactions, how they've been distributed, what's happening, where it's going, and accounting for all the diffusion mechanism there. I don't see a problem.
Okay. Actually, in normal of, in SWRO plants or in our combined cycle plants where we have seawater intake systems, or we use CFD modeling to model the behavior of sumps, large pumps and the sump models. So in the similar way, have you done any kind of study for the green hydrogen plant where the owner has asked the EPC contractor to model the performance based on the CFD of the electrolyzers?
So I'm not sure I understood the question, because you start talking about the pumps and then you
Yeah,
went to.
I was just giving the example, like in our SWRO desalination plants, we have a large intake systems, okay, and
Okay.
we usually use the CFD modeling to check whether the pump performance, because these are very high capacity, 40-50,000 meter cube per hour pumps, vertical pumps, whether these are operating perfectly or not, whether the some model, we need to change or not. So similar on that way line is there, and these studies are normally governed by the owners. The owner asks the EPC contractor to do these studies. Okay, so on the similar way, is this kind of studies, some kind of studies have you done for the electrolyzers also, like where the owner has asked the EPC contractors to follow these kind of CFD studies for the electrolyzers?
I typically, there are different groups that work with that, and when it comes to coupling different solutions, how different things are working. I think I showed one of the slides. Let me just, if I'm still sharing it, for the system of plant. Okay, you do have electrolysis for specific conditions, so what kind of similar to fuel cells of what input that needs to be done. So it's not really coupled all together, but I think the income for water is just one of the input, and it becomes a bit of a system regulation or control loops that are being used to adjust one to the other.
Okay.
The good thing about electrolysis is that usually it's performed on a relatively steady state regime in comparison to the fuel cells, that where the driving cycle might drive them to into different corners of operation and of the polarization curve. With electrolysis, typically it can change, but most of the time it works at the pre-designed sweet spot where it's most efficient and where everything is uniform and steady.
Okay. Thank you.
For
That's
fuel
all from
cells,
my side.
for fuel cells, there's a bigger problem, of course. That's why we need to come up with a system level approach where might need to be adjusted dynamically.
Okay, I think we've got time for a last question, if there's anything else from the attendees. Doesn't look like that. There's no hands up. You can just unmute yourself if you have any further questions. I guess there's nothing else. I think you've answered all the questions that the audience had at this time. Alexei, thanks a lot for that. What we will do, we will share the recording, send certain sections of the presentation, and then we will, thanks for completing the poll that we had. We will follow up on that and respond according to, based on your requirements moving forward. So without that, enjoy the rest of the day. Have fun, and thanks a lot, Alexei. Enjoy your day as well. Thank you.
Thank you very much.
Thanks. Cheers.
Bye-bye.
Thanks. Bye-bye.
Thank you. Bye.
Like,
So we can stop recording, I think, Lars.